Hello, everyone. This is Lianrui from Johns Hopkins University. Today, I'm going to present our recent work entitled Disentangling a Single MR Modality. An MR image is generally assumed to be a function of the latent factors A star, which is anatomy, and C star, which is contrast or acquisition parameters. The goal of disentangled representation learning is to learn an inverse scanner function so that we can have an estimate of the latent factors A and C, and also we would like A and C to be independent with each other. These disentangled representations have shown to be very useful in multiple image analysis tasks, including segmentation, classification, and domain adaptation. In this presentation, I'm going to mainly focus on last two applications, domain adaptation and image-to-image translation. Disentangling A and C, unfortunately, is a non-trivial task. Previous work has already shown that theoretically that we need inductive bias to actually achieve disentanglement. There are mainly two ways to introduce inductive bias. The first one is labels, such as manual delineations of certain anatomies. And the second way to introduce inductive bias is to use paired data. Multi-model images of the same anatomy are the most commonly used paired data to achieve disentanglement in medical imaging. These images are assumed to have the same anatomical information and different contrast information. However, these multi-model paired data and labels generally introduce an extra burden in data collection. This is not ideal in many applications. Motivated by this, we propose a single model disentangling framework. Our method introduces inductive bias from a very special type of paired data to the slices of the same 3D volume. These images are assumed to have the same contrast but different anatomy. And this is the first contribution of the proposed method because we have reduced data requirements compared with existing disentangling methods. So given these images, how can we achieve disentanglement? We first introduce two encoder networks, the anatomy encoder EA and the contrast encoder EC. EA extracts anatomical information from image X and EC extracts contrast information from image X prime. Again, images X and X prime, they're just two different slices of the same 3D volume, so we don't need paired multi-model images for training. We also have a decoder network that combines these latent representations A and C to generate a synthetic image X hat. So given this framework, we have three objectives. The first one is that we would like X hat to be as similar as possible to real MR image X. The second goal is that we want to have A to represent anatomical information and C to represent contrast information. And lastly, we would like A and C to be independent with each other to achieve disentanglement. These objectives can be mathematically represented into three terms, and we show that they are optimizable by loss functions. The first one is just an L1 loss between X hat and X, and this is typically used in image synthesis works. The second one is to maximize the mutual information between X and C. Because X and X prime, they only share the contrast information, and C is learned from X prime instead of X. Maximizing this mutual information between X and C essentially would encourage C to capture contrast information. We also show in the paper that this mutual information maximization can be achieved by maximizing the lower bound of IXC following reference number 1. However, the current community does not have a good way to directly minimize the mutual information between two arbitrary variables. So the second contribution of this work is that we propose a new way to explicitly minimize the mutual information between A and C so that we can encourage disentanglement. To minimize IAC, we propose a distribution discriminator. We call it UAC. UAC receives both A and C as its input, and it's going to produce 1 if the input AC pair is from the same subject, and it's going to produce 0 otherwise. We show that UAC essentially learns to distinguish if the input AC pair is sampled from the joint distribution PAC or the product of the marginals PA times BC. Because we learn A and C from images X and X prime, we sample the joint distribution by selecting samples when AC are from the same subject. We achieve sampling PA times BC by shuffling along the batch dimension. During minimizing IAC, the contrast encoder EC is also detached from the computational graph. So there is adversarial training between EA and UAC. Also in the paper, we show theoretically that EA achieves its global minimum if and only if A and C are perfectly disentangled. We also propose a novel metric to quantitatively evaluate disentanglement. This is also the third contribution of the work. We defined a ratio RIAC, which is IAC divided by HC, and HC here is the entropy of variable C. RIAC, first of all, has a nice theoretical meaning. It is the proportion of information that C shares with A. It is also bounded, meaning that 0 is the perfect disentanglement and 1 represents the worst scenario for disentanglement. And lastly, we show in the paper that this ratio can be estimated following references number 1 and number 2 below. We evaluated our method in 2 different tasks. The first one is brain MR harmonization, and the second one is cardiac MR segmentation. For the first task, brain MR harmonization, we used the proposed single model disentangling framework to harmonize multi-site MR images by conducting image-to-image translation. We want to see here if the harmonized images between sites A and B are similar as the images that are actually acquired from the 2 sites with a group of traveling subjects. We first compare our method that is trained only on T1 weighted images with CycleGAN. We show that our method achieved superior performance with statistical significance. We then compare our method with existing disentangle methods that rely on multi-model paired data, meaning T1 weighted and T2 weighted images of the same subject for training. And our method only trained on T1 single model has similar performance than multi-model based disentangling methods. And lastly, we conducted an ablation study to experiment the effect of paired multi-model images. We found that if we introduce 50% paired T1 and T2 weighted images, our method can have even better performance. But if we train our method using all paired multi-model data, our result becomes worse. We think this is an interesting and kind of surprising observation, and we will discuss this in the next slide. We then asked ourselves, do we learn better disentanglement? And how do we explain the performance decrease when we use 100% paired data? We first calculated the proposed RIAC to quantitatively evaluate disentanglement. We see that all 3 ablations achieved superior performance in terms of disentanglement compared with existing methods. We also see that as we introduce more paired data, A and C become more entangled. We think the reason here is that these paired multi-model images, T1 and T2 weighted images, are not ideally paired. There are subtle anatomical differences between those images, and this effect is also reported by other researchers. In addition to the brain MR harmonization, we further evaluate the proposed method in the cardiac segmentation task following the M&M challenge. Unfortunately, we don't have enough time to go through every detail of this experiment, but we provide detailed numerical analysis in the paper. Some key result we got from this experiment is that the domain shift can be reduced with the proposed method. In conclusion, we propose a novel single model disentangling framework that is, number 1, requires less data for training, and number 2, it has superior disentanglement with the mutual information minimization. And number 3, we have a new metric to quantitatively evaluate disentanglement. We also demonstrate that using non-ideal paired data may have negative effects in disentanglement. And finally, we would like to thank BLSA participants and all of our collaborators. For further questions, please feel free to contact me with the following email address. And thank you for listening.